Hi, and welcome back to Mr. Curl's Classroom. Today we're going to talk about the continuously compounding interest formula, also known as PERT. So let's go ahead and check it out. Okay, so we're back at our finance formulas here, and remember all of these are really derived from exponentials. Our parent exponential here, which is y is equal to a times b, some kind of base, to the power of x, and where b is what we're multiplying by over and over again. How many times? Well, x number of times. That's what makes it an exponential. And so in our last lesson, we covered the simple interest formula. Let's go ahead and get these names up here. The simple interest formula. And we showed that really this is the same thing as y is equal to a times b to the x. It's just that now we're going ahead and putting in some of these explicit variables like r, for example, for our rate, or t for our number of years. Then we went ahead and learned how to compound our rate, our interest rate, n number of times. And so that basically just means that we're going to divide our rate over n number of times, how many times we're going to compound it per year, which also changes our how many times we're going to multiply by that rate, because we're compounding, and not just once per year, but n times per year. And now today, what we're going to be interested in is this one right here, which is our PERT formula, or our continuously compounding interest rate formula. All right, so we're going to kind of build up, because really using this formula is extremely easy, but understanding what each piece means is a little bit more challenging. And the last thing I want to note here is really that I just want to recall that all of these formulas are derived, and they are the same as our exponential here. It's just that now we're giving different variables to meet different specific situations. All right, so anyways, so we came up with our simple interest formula, and then we went ahead and derived our compounding interest formula from that. And now from our compounding interest formula, we're going to end up coming up with our continuously compounding formula. And one last thing, just to remember what these actually stand for, these variables. Remember that A stands for the final amount, P stands for the principal amount, or the initial amount. R is going to be the rate, which is always expressed as a decimal. T is going to be our time in years, and if we're compounding, N is going to be the number of times we're compounding that rate over 1 year. All right, so let's go ahead and answer like the first question here with this formula. And the first question is probably, well, I know what P is, I know what R is, and I know what T is, but what is E? What variable is that? Well, actually, E is not a variable. E is an actual number. So let's go ahead and bring that up. In fact, it is this long decimal number. In fact, it's an irrational number, and it goes on forever with no pattern. It's very similar to pi in that way. In this case, though, pi is 3.14159 going on forever, in no particular pattern. E is 2.718, and actually I think I have a typo in here. I think it's 18248, so on and so forth, going on forever. And so this is actually a really, really important number, just like pi is an important number. And so it does have a name. This is called Euler's number, and it's named after Leonhard Euler, and he is one of the most prolific, if not the most prolific, mathematicians of all time. And so he named this E, and it's not actually after his last name. It just happened to be the next letter that he was using in his notes. But and a little factoid here is he also named pi. Pi was known for a long time before Euler, but I'm pretty sure it was known as Archimedes' constant. But anyways, Euler went ahead and used the Greek letter pi in order to make writing out mathematics and utilizing pi easier. Well, we do the exact same thing with E. So remember, pi and E are not variables. They are specific numbers, and they happen to be irrational. So they go on forever with no particular pattern. Now, Euler's number is it pops up all over in mathematics, just like pi does. Right now, we're talking about compounding interest, but it also shows up in things like probability theory, the standard normal distribution in statistics, optimal planning problems, probability, really all over the place. E pops up just like pi pops up in different places. And then really the last thing I want to mention, just because now that you know what pi and e are, and they're so important, is I kind of want to show you what Euler's identity is, because it really has nothing to do with today with using this PERT formula, other than e happens to be in it. But I do want to talk about it. Now that you know what e and pi are, we have Euler's identity, which is e to the I pi plus 1 is equal to 0. And this is commonly referred to as the most beautiful equation in all of mathematics. And there's a good reason for that. This equation it contains 5 numbers, but they all come from different walks of life, and they show up in many different areas all over mathematics. And in fact, many areas that seem like they're not connected. And what's truly incredible about this shows that they are connected. And in fact, it's connected in this very, very simple little tight equation. And it's pretty incredible that you can take e, which is an irrational number with no pattern that goes on forever, and then take it to the power of I, which is an imaginary number, the square root of -1, times pi, which is a different irrational number that goes on forever with no pattern. Add 1 to it, and you end up with 0. And so 1, by the way, is the multiplicative identity, and 0 is the additive identity. So together, these 5 numbers are the most important numbers in mathematics, and they're all tied together, and they also tie together different areas within mathematics. And it's connecting these different areas as it's shown right here in this identity. So areas in mathematics that might seem very disconnected are actually very connected. Okay, so let's go ahead and approximate e. So just like pi, there are many, many ways to go ahead and approximate it or calculate an approximation of that number. So we're going to go ahead and use our compounding formula. A is equal to p times 1 plus r divided by n all to the nt. We're going to use this compounding interest formula in order to come up with e. And how are we going to do this? Well, we're going to simplify this formula as much as we possibly can by setting the principal to be 1, the rate to be 1, and the time in years to be 1 as well. And so when we set all of these variables to 1, this simplifies to be 1 plus 1 over n all to the n. And what we're going to do in order to get closer and closer and closer, never really getting to it, but getting closer and closer and closer to this number, is we're going to continuously increase n. And so let's go ahead and bring up a table and see what happens. So remember, this is compounding over 1 year. So if n is 1, that means I'm compounding yearly. And so we're going to plug in 1 for n here. And really that ends up being 1 plus 1, which is just 2, which I guess is kind of close to 2.718, so on and so forth. But then once we start increasing n, let's see what happens. So if we compound semi-annually, then n is going to be 2, and we end up with 2.25. So it's a little bit closer to 2.718. Quarterly, or 4 times per year, n is 4. We end up getting a little bit closer, 2.44, so on and so forth. Monthly, 12 times per year, 2.61. Weekly, 52 times per year, 2.6925. We're getting really, really close to this 2.71. Let's keep on going and keep on increasing n as much as possible. If we compound daily throughout the year, well, then that's n is 365 days in a year. Well, now we get 2.71. So we've got 2.71. We're still off a little bit with the 4. Hourly, well, there's 8,760 hours in 1 year, 2.718 every minute, 525,600 minutes in a year. We're getting closer. Every second, 31,536,000 seconds in 1 year, and even every half second. Well, you can double that. And so you can see if we're compounding down to the half second, right, we're applying that rate. Then we're getting 2.71828, and we're getting really, really, really close to this. Now, how close can we get? Well, we need to continuously increase n as much as possible. In fact, n is going to approach infinity. And as n approaches infinity, then our answer is going to approach the true value of e. Now, can we ever get there? No, not really, because this goes on forever and ever and ever. Okay, so last question before we actually apply this. In the beginning, we showed those finance formulas, and we went from the compounding interest formula to the continuously compounding formula. Now, the question is, how do you get from here to here? Because previously, when we went from just an exponential to the simple interest to the compounding interest, those were like we could actually follow where those came from. In this case, it's really not so obvious, and you do need to know just a tad more mathematics in order to understand how to get from the left side to the right side, but really not that much more. Really, all that's necessary to know is a little bit more about logarithms, and then also how to solve logarithmic and exponential equations algebraically, just using properties of logarithms and exponentials. Other than that, you do have to have a basic understanding of limits, but that is something that you'll learn in pre-calculus next year, which is really not that big of a deal. So what I'm going to do now is I'm just going to go ahead and throw this derivation up on here. And even though you may not really be able to follow these steps as of right now, really probably just within a few additional lessons, once we get into logarithms and solving equations and doing some algebra with those, you will probably be able to kind of understand these steps as we go through. But either way, this is these are all the steps to derive the formula, going from the compounding formula over to the continuously compounding. And again, this is simply just applying algebra. Okay? All right. Now, let's go ahead and we'll cap this off with just an example here, and you're going to see how easy it is to actually apply the continuously compounding formula. So here's our situation. You're going to start with a savings account. You're going to start a savings account at your bank. The account has a 3.5% interest rate that is, and this is the important part, compounded continuously. Right away, that tells me I'm using PERT. Anyways, if you initially have deposit $1,000 and you never touch the account, how much money will you have after 30 years? All right, so let's go ahead and use this formula. So first of all, we'll highlight our important pieces, and really by far, again, this compounded continuously. If you see the word compounded, then you know you're going to use the compounding formula. But if you see compounding continuously, then you know you're going to use the PERT formula. Okay, so let's just remind ourselves, here's the formula right here, P times E to the RT. Remember, E is not a variable, it is an actual number. Luckily, our calculators have that number stored, which we'll see here in a second. So when we go ahead and pop in our values, well, we're going to start with $1,000. Our base is E, and our rate is 0.035, just converting that 3.5% into a decimal. And T is going to be 30 years. Now, in order to plug this into our calculator, we do need to know where E is on there. So let's go ahead and check that out. So on any type of TI calculator, TI 83, 84, probably even an 86, it's going to be right above the division sign. So this might be hard to see, but if you have your calculator, go ahead and take a look. It's actually second and then the division sign. So this blue one right here is the letter E. In fact, it is right below the letter pi right above it. So anyways, so all calculators, any scientific is going to have both pi and E. All right, so let's go ahead and plug this in. And so once we do plug this in our calculator, we get 1,000 times E to the 0.035 times 30, and we end up getting $2,857.65. All right, so there we go. There's our lesson on the continuously compounding interest formula. Hopefully you found this helpful, and hopefully you understand that it's easy to apply. It's a little bit more difficult to understand where it comes from. All right, so anyways, hopefully this was helpful, and I hope to see you in the next one. Bye now.